Well, hello friends, welcome to engineering tutorial. Today we are going to discuss some of the introductory and basic concepts of circuit elements and energy sources. Now this topic or these concepts which I am going to discuss are particularly related to basic electrical engineering, or which we call circuit theory or network theory. So let's get started. We are going to start uh, this video with the concept of charge and current. Now, electric charge is perhaps the most basic and fundamental concept involved in electrical engineering or circuit theory. Now, what is electric charge? Now, electric charge is a property of atomic particles or any matter which determines its electromagnetic interaction or electromagnetic behavior. Electromagnetic interaction means the way it responds to an external electromagnetic field. It can be explained as each and every matter, when placed in an electromagnetic field, experiences a force, and as a result it moves in a particular direction. Now this experiencing of force and the movement due to this force is governed by electric charge or the movement of electric charge. So charge governs the electromagnetic behavior, electromagnetic interaction of substances or materials. Now the unit of electric charge is coulombs. Now from high school elementary physics we learned that the charge on an electron is given by 1.602 into 10 to the power minus 19 coulombs. While conversely, we can say that 1 coulomb is equal to 6.24 into 10 to the power 18 electrons. We just did the reciprocal of this by unitary method. Now, charge are of two types, or they can be classified into two categories. Now, positive charge, which we know as protons, and negative charge or electrons. Now we know about protons from the same high school physics. The protons and electrons contribute to the electrical neutrality of matter. And there is an additional thing called neutrons too, but we are not going to discuss about that here. We are going to limit our discussion up to these two entities, positive charge and negative charge. Now the law of conservation of charge states that charge can neither be created nor be destroyed. It can only be transferred from one point to another. So we cannot create or destroy charge. It can only be transferred or moved, and this transportation or movement of charge contributes to every electrical behavior of circuits or electrical behavior of materials. It is governed by the movement of charge. Now we will see how this happens. Next we are discussing is current flow due to charge. Now let us imagine we connect a conducting wire to a battery, and apply a voltage from the battery. Now the battery creates an electric potential or electromagnetic field. We just discussed about it. So as a result, the charges in the wire or the material of the wire are forced to move. Now how they are going to move? The positive charge, let me show you a figure, you will understand it better. Now here, this wire, we have just enlarged it. This wire is connected to a supply battery here, and as a result, the charges, here we have shown only electrons, both the charges, positive and negative charge, are forced to move. Now in which direction they are going to move? Now the negative charge or the electrons are forced to move towards the positive terminal of the battery, while the positive charge, the protons, move towards the negative terminal. Now we have not depicted the protons or the positive charge, but it is, they move towards the negative terminal, they move towards the opposite ends, opposite polarities, positive towards negative and negative towards positive. Now this movement of charges in opposite directions towards the opposite terminals of the battery causes the flow of electric current. So electric current flows due to migration of electrons. Now the direction of flow of electric current is in the direction of movement of the positive charges, that is opposite to the direction of flow of electrons. So electric current or conventional electric current flows opposite to the direction of flow of electrons. So now how we are going to quantify the magnitude or the amount of electric current flow? Now the amount of current in the circuit is given by the expression charge transferred, the total amount of charge in coulombs transferred by time taken, or it is the charge transferred per unit time. It is also given in derivative or differentiation form as electric current I is equal to derivative of charge as a function of time with respect to time, dq by dt. Now unit of electric current is amperes. Next we are going to discuss is voltage. Now earlier we discussed the movement of charge in a conductor due to the electromagnetic field created by the battery. So here we are going to discuss that in order to move a charge in a conductor in a particular direction, some amount of work or energy transfer is required. Now this work or energy transfer is performed by an external electromotive force. Now this electromotive force or EMF is called as the voltage or potential difference. Now a major source of potential difference in electrical circuit is a battery. A battery, it supplies the required electromotive force to facilitate the movement of charges, which in turn produces current in the circuit. So we can define the voltage between two terminals as the amount of work done, W, to move a charge or unit charge from one point to the other. So it can be expressed in mathematical form as total work done W by total charge transfer, the work done per unit charge. It can also be expressed in differentiation or derivative format as voltage is equal to derivative of work done with respect to charge, dW by dQ. Now the unit of voltage or potential difference is volts. Next we are going to discuss about energy and power. Now energy and work done are both the same. Some amount of energy transfer or work has to be done to move a charge from one point to another. And the unit of energy we all know is expressed in joules or calories, kilocalories, whatever it is, but in electrical circuits it is expressed in joules, the amount of work done or energy transfer done. Now power is the rate of absorption or expending, the rate at which energy is expended or energy is absorbed or work is done is called as power. Now the unit of power is watts. It is quantified in terms of watts. Now we can express power as total work done W by total time taken, work done over a particular interval of time t. And it can also be expressed in derivative or differentiation form as work done as a function of time with respect to time equals to dW by dt. Now this expression can be broken down into two parts, dW by dq into dq by dt, which will give the same expression dW by dt when multiplied together. So dW by dq, work derivative of work done with respect to charge, is nothing but the expression for voltage, while dq by dt, or the derivative of charge flow as a function of time with respect to time, is nothing but the expression for current. So power is nothing but the product of voltage and current in a circuit. Next we are going to discuss about resistance. Now what is resistance? As the name itself suggests by its literal meaning, it is that property of a material or a substance by virtue of which it opposes or restricts or obstructs the flow of electrons in a circuit. It resists or it opposes the flow of electrons through it. In other words, it obstructs the flow of current through the material. So the unit of resistance is ohms. Now the value of resistance is derived or obtained from Ohm's law. That's why the unit of resistance is ohms, because it's named after Ohm's law. Now Ohm's law states that all other physical conditions remaining unchanged, the current through a conductor is directly proportional to the potential difference applied across it. The current flow through a conductor or a material or a substance is directly proportional or is directly related to the potential difference which is being applied across that conductor. So of course V is directly proportional to I, so V is equal to IR. Now here the R is a constant of proportionality called as resistance. Now this is resistance. So let's see it from a graphical point of view. Now here there are two plots of two different substances or two different materials. Now the red plot, pay attention, in the red plot a large increase in voltage, this one, gives us a small change in current. Here current is being taken in x-axis, while voltage applied is given taken in y-axis. So a large increase in voltage, applied voltage, brings about a small change in current. Now we know that resistance is equal to voltage by current. So of course a large value of voltage in the numerator brings about higher value of resistance. But in the blue plot, a small change in voltage brings about a large change in current. So it is an indication of low resistance. So at smaller potential applied across this, the material, there is a large value of current. So it is an indication of low resistance. Now in Ohm's law we came across the physical conditions of a material. So the resistance of a material can also be given or can be expressed in terms of its physical conditions. Now what are those physical conditions? Now resistance of a material is equal to rho into L by A. Here rho is the resistivity of the material, which is that property which actually opposes or restricts the flow of current through the material. L is the length of the material, whereas A is the cross-sectional area. So here we can infer that the resistance of a material is directly proportional to resistivity and length, and is inversely proportional to the cross-sectional area. Now this is a depiction of a resistance, the symbol of resistance, and this is the current flow, and it is the battery which is the source of electromotive force or potential difference. Now when electric current flows through any material, heat is generated due to collision of the free electrons which are responsible for current flow with the atoms in the material. It produces heat energy. So of course there is some absorption of power by the resistor, which is equal, we all know power is nothing but the product of voltage and current, V into I. Now here there are two ways in which this expression can be formed: by breaking V as IR into I, which is equal to I square R, or by breaking it in as V into V by R. V by R is for I, which is equal to V square by R. Now unit of power is watts, we all know. So next is the energy lost in the form of heat is nothing but the work, the energy. It is the product of power into time, or the integration of power over a certain interval of time dt. Now the unit of energy is joules. Okay, the next concept which we are going to study is the property of inductance. Now inductance is the property of a material by virtue of which it opposes or restricts any change in the magnitude and direction of electric current passing through it. So it opposes any change in magnitude and direction of flow of current. Now unit of inductance is Henry. Now a wire of a certain length, when twisted, see here, a wire when twisted behaves as the simplest of inductors. Now generally the wire is wound over a metallic core, generally iron or ferrite, and in some cases the wire is wound without any physical core. Here air behaves as the core. The free space which contains air behaves as the core. So it is a simple inductor, depiction of an inductor. It is the schematic diagram of an inductor. This is the symbol of an inductor coil which applied to a AC voltage source and a current flow in the circuit. Now whenever a current flows through an inductor circuit, it magnetizes the coil. It produces a magnetic field. So this induces an EMF or potential in the coil. Now this EMF is directly proportional to the rate of change of magnetic flux linking with the coil. So it can be expressed as E, the EMF or the voltage which is produced, as the rate of change of flux with respect to time, d phi by dt. Here we have not taken that, but remember it's also important. EMF can also be expressed as the rate of change of magnetic flux linking with the coil with respect to time, d phi by dt. But here we have taken this expression. The EMF induced in the coil is directly proportional to the rate of change of current with respect to time multiplied with another constant of proportionality, L, which is called as the coefficient of self-inductance or simply inductance. Now the negative sign indicates that this EMF induced in the coil actually opposes or counter effects the applied voltage. That's why it's the negative sign is there. So the voltage induced in the coil is directly proportional to the rate of change of flow of current through the coil and is expressed as L di by dt, where L is the coefficient of self-inductance, which is the constant of proportionality. So the current through the inductor can be just found out by reversing this equation. I is equal to integration of the voltage 1 by L over a particular interval of time dt, 1 by L integration of V over a particular interval of time dt plus the initial current at time t equals to 0. So this is the expression for current flowing through the inductor. Now there is another formula or expression for inductance in terms of physical dimensions and some physical parameters. The inductance of a coil can also be expressed as n square into mu into A by L. Now here n is the number of turns of the coil, the inductor coil, which is wound over the core. Mu is the permeability of the coil. Now it is the ability of the material to get itself magnetized by an external magnetic field, or the extent to which it can be magnetized with a magnetic field or flux of certain intensity or value. A is the cross-sectional area of the coil and L is the length of the coil. Same here, we are also going to discuss the power absorbed or the heat energy lost in the inductor coil as the product of voltage and current. Voltage we all know, L, derivative of current with respect to time, L di by dt into I. The unit of power is watts. Similarly, energy, product of power and time, which is equal to P into T equal to VIT, which is equal to integration of Li di by dt into dt, which is dt gets cancelled, which is equal to integration of Li di, which is equal to half Li square. Unit of energy, joules. So here it is in derivative form, L di by dt, which is the derivative or differentiation of current as a function of time with respect to time. So next, the concept which we are going to discuss is the property of capacitance. Now the capacitance is the capability or the property of an element to store electric energy in the form of electric charge. Now a capacitor in simplest form can be depicted as two parallel metallic plates separated by an insulating medium. Now this insulating medium is called as the dielectric. This dielectric is a bit different from other normal insulators. It does not permit any flow of current through it, but it is capable of charge separation or to permit the flow of charges through it. So a dielectric is an insulator having the ability of charge separation. Now these two metallic plates are separated by a certain distance d and have a particular cross-sectional area A, and they are connected to the different terminals or the two terminals of a battery. One is connected to the positive terminal while the other is connected to the negative terminal, the battery or the voltage source V. So the capacitance can be quantified by the expression which is equal to charge stored by applied voltage. Charge stored is equal to Q and voltage applied is equal to V, or it is the measure of charge stored per unit voltage applied. The unit of capacitance is farad, F. Now here is a slight expression for the voltage and current through a capacitor. Now we know C is equal to Q by V, so Q is equal to C into V. That implies we can write I, which is equal to derivative of charge Q with respect to time, which is equal to C into derivative of voltage as a function of time with respect to time. I is equal to C dV by dt. I is equal to here dq by dt, which is equal to C dV by dt. The differentiation of voltage as a function of time with respect to time multiplied by the capacitance. Similarly, just by reversing the above equation, we can get the voltage expression in a capacitor, which is equal to 1 by C integration of current over a specific interval of time dt plus the initial voltage in the capacitor at time t equals to 0. Same power absorbed by the capacitor is the product of voltage and current is equal to V into C dV by dt. Here we just derived the expression for current through the capacitor. Now energy stored in the capacitor is the product of power into time integration of P over a specific interval dt is equal to V C dV by dt into dt. V into I, remember, VIT. This one is equal to VIT, which is equal to V into C dV by dt for I and dt. So it is equal to half CV square, the energy expression. Now here is another expression for capacitance of a parallel plate capacitor in terms of its physical dimensions. It is expressed as epsilon 0 epsilon r into A by D. Here epsilon 0 and epsilon r are absolute and relative permittivities of the dielectric medium, which is the ability of the dielectric medium to facilitate the movement of charge. Now A is the overlapping area of the two plates, the area of the two plates which lie over each other, overlapped over each other, and D is the distance between the two plates we just saw here. So here it is the depiction of a parallel plate capacitor. It is the dielectric material. These are the two plates. This is connected to the positive end. This plate is connected to the negative terminal of the voltage supply. So as a result, the negative charge moved towards the positive plate, the positive charge moved towards the negative plate. And this separation of charges produces an electric potential within the capacitor or a voltage within the capacitor. So this is the basic principle of operation of a capacitor. So here I have discussed with you some of the basic concepts related to circuit theory or network theory, and I hope you like this video, and please subscribe my channel Engineering Tutorial for more such interesting videos on electrical and electronics engineering. Thank you very much.